everyone, welcome to the first lecture of control system. This video will contain all the basic information which you need before going to the subject. So it is basically an introduction type video. So let's take this example of a liquid level control system whose main objective is to keep the water level in the tank at height h. We will study this control system in just few seconds. So in control system, there are basic two types of control loop configuration. One is closed loop and another is open loop. And then we have different modes of controller like proportional mode, proportional plus integral mode, and proportional plus integral plus derivative mode, and so on. There are many types of such controllers which you will study in this course later. So let's start with the closed loop configuration. This was your liquid level controller. So here this is your automatic controller and this is your output. So here it is taking feedback from output and then comparing it with a set point, and then accordingly it is adjusting this control element which will help in maintaining this height edge. So you can see that this is a closed loop type of configuration. So in closed loop configuration, the changes in the output, so this was your output, and here the changes are measured through the feedback. So this is your feedback, and then they're compared with the input or set point. So in this case we have set point, and this is done to achieve the control objective, which is to maintain height h using this control element present here. So there it was a physical diagram, and here we have a flowchart diagram of what is happening. So here we are taking feedback from the output. It is measured through a level transducer or any sensor, and then it is given back, and here it is compared with the set point or the input or whatever you have there to measure things, and then accordingly it gives output, and then automatic controller is there. It processes the output of a comparator and give the required control action, which is now being executed by this control element. And now this control element is adjusting this height of water in plant tank through inlet, outlet, or whatever it can do to control the height, and thus you get the output again. Now this path is known as feedback path, and it is noted usually by HS, and this path is known as forward path and it is noted by GS. So controller is what? It is an automatic device with error signal ES as input. So this is your ES. It is the error signal. Why? Because it measures the error between the set point and the output. And controller output is PS. This is your PS, and it is affecting the dynamics of plants. See, through control element, it is the affecting of dynamics, means plant tank height, to achieve the control objective, which was to maintain height h. Therefore, controller output PS is a function of E, and E is what? Steady state error. We will understand the concept of steady state error in further lectures. So this big flow chart can be reduced in this flow chart. This is a basic block diagram here, where all the elements present in the forward path are denoted by a single element GS, and all the element present in feedback path is noted by HS, and this is your input RS, this is your output, this is your error signal, and this is your feedback signal. So this was your simplified block diagram. So here we can see that this error signal is nothing but RS minus BS. RS is input and BS is feedback, and then output is GS into error signal. Therefore, in place of error signal, we can write CS upon GS. This is output upon forward path element. And then we have this BS. BS is what? CS into HS here. Output into feedback path element. So we will write HS into CS in place of this BS. And now here we take CS common, and thus we get CS is equal to RS into GS 1 plus GSHS. So this whole block diagram can be simplified again in this form, and this is your basic block diagram for a closed loop configuration where GS is your forward path element and HS is your feedback path element. One thing to notice here is that this feedback element is added negatively here. See, this is minus, and therefore due to this minus sign we are getting here plus. If the feedback element here is it plus, means it is not subtracted, it is added, then in place of plus here we will get minus. You will understand these concepts later. Now you have to just remember this, that you have subtracted the feedback element, that's it, and this results in positive sign here. So now we will see the sensitivity analysis. So here let alpha be a variable whose value is changing and beta is a variable who is changing the value of alpha. Then sensitivity of alpha with respect to beta is equal to percentage change in alpha upon percentage change in beta. So when we put the formula, we have this. We have change in alpha upon alpha and this upon change in beta upon beta. So we get this basic formula of sensitivity, which is beta upon alpha and then partial differentiation of alpha with respect to beta. This is the basic definition of sensitivity. You have to remember this because all the other derivations are just extended version of this formula. So now we will see the sensitivity of closed loop control system with respect to disturbance in forward path element GS. So GS is your forward path element and it is your beta, and here alpha is the closed loop control system. We have denoted it by MS. So the value of MS we have just calculated is GS upon 1 plus GSHS, and then this is the sensitivity formula. Here we will put all the value of alpha and beta. So we get sensitivity is equal to GS upon MS and then partial differentiation of MS with respect to GS. So first we will calculate this thing and then we will put the value of this here. So here we will put the value of MS. So this is your MS and then we will calculate its derivative, and in this case since it is partial differentiation, HS is considered as constant, only GS is variable. So we get the partial differentiation of MS with respect to GS is equal to 1 upon square of 1 plus GSHS. So now we will combine the results of all the three equations and put here in this formula, then we get this. So this get cancelled and here we get sensitivity is equal to 1 upon 1 plus GSHS. Now this formula you can remember for answering questions quickly in 1 second, because it is asked like this only, that find the sensitivity with respect to forward path. Also 1 plus GSHS, this denominator factor is known as noise reduction factor or return difference, and here you can see that sensitivity is the inverse of this factor. You can say that it's another name for sensitivity, as it can be asked for exam to confuse you. Now we will again calculate the sensitivity of closed loop control system, but here with respect to disturbance in feedback path element HS. So here everything will be same, only beta will be changed. So beta is here HS, and now we will calculate sensitivity of closed loop control system with respect to beta, which is HS. So first we will have here the partial differentiation of MS with respect to HS. So since it is the partial differentiation, so here we will consider GS as constant, only HS will variable. So here we get this as a partial differentiation, and now we will put all the things together in this formula and we get this. Since sensitivity is a mod value, so we can ignore this negative sign. So we can say the sensitivity of closed loop control system with respect to feedback path element is GS into HS upon 1 plus GSHS. And we also know that sensitivity of closed loop control system with respect to forward path element was 1 upon 1 plus GS into HS. So you can see that this value is greater. Therefore, we can say the control system is more sensitive to changes in feedback element than in forward path element GS. In control system, more sensitivity is better because it means the system gains back to its original position after incoming disturbance. But for control instruments, means for measurement and all, less sensitivity is preferred because there it means small value of input for which it will give output. So it's a whole different thing you will see in measurement of electrical instrument. But here in control system, more sensitivity is better. Okay, so after taking all the examples of closed loop control, now we have this open loop control system. So this is your input, this is your output, and there is no loop. It is open loop control system. Output here is taken but just to measurement or just for having record. Nothing is given here feedback. So here there is only one path, which is forward path, and it is noted by GS into TS, and both are just some functions or a part of a forward path. So now MS is what open loop control system, and it is noted by GS into TS. So it is your alpha, and beta is what? GS. So now we will calculate the sensitivity of open loop control system with respect to forward path element. So this is your formula, and we will put everything here. So partial differentiation of this open loop control system with respect to GS is what? Nothing but equal to TS. You can see from here. So now we will combine all the results, and here we get that the sensitivity of open loop control system with respect to forward path element is 1. So it is highly unstable when any disturbance occurs. So now we can conclude that open loop control systems are conditional control system. See, it is conditional because it is formulated under the condition that the system is not subjected to any type of disturbance. Here we have assumed that there is no type of disturbance, and thus we are using this open loop control system. And since here we have assumed that they are not subjected to any type of disturbance, therefore performance analysis is not applicable for these systems. Hence they give out a stable operation. This whole thing is imaginary thing. So if there is no disturbance, then obviously the system will be stable. But practically open loop systems are highly unstable when any disturbance occurs. Okay, now we will move forward to the concept of transfer function. So transfer function is a mathematical model of representing the control system relating the input and output in the form of ratio. So transfer function is basically the ratio of output to input, basically in S domain. So here we have this sample transfer function. You can see here. It can also be written as ns upon ds, where ns is your numerator and ds is your denominator. It is nothing new. So here this k term is called as system gain, and then when you put the numerator equal to 0, then what we get s is equal to minus z1 and minus z2. Therefore z1 and z2 is equal to zeros. And now we will put whole this thing equal to infinite. Infinite is what? 1 upon 0. Means we will put denominator is equal to 0. Then we get s is equal to minus p1 and minus p2. So p1 p2 are the poles. This is your s plane where zeros are denoted by this and poles is noted by a cross in time constant form. So this is a time constant form. See the difference. Here it is written s plus z1 and here it is written 1 plus tas. So this is a time constant form. And now the resultant gain, this system gain is also known as DC gain. This is very important thing to remember. To find DC gain of a system, you have to convert the transfer function into time constant form like this. Okay, so here we have four basic types of signal functions: impulse signal, step signal, ramp signal, parabolic signal. Impulse signal is denoted by a delta t, which is 0 at t not equal to 0. So it is 0 everywhere here and here, but at t is equal to 0, it is infinite. You can see from here. And the Laplace transform of this delta t is 1. Then you have this step signal. So step signal is denoted by ut. Therefore, ft is equal to aut, and ut is equal to 0 at everywhere t less than 0, and for t greater than 0 means here it is 1. You may think, what is the value of ut at t is equal to 0? Well, it is not defined. You can see that here it is changing. Therefore, it is not defined here at t is equal to 0. So here we haven't considered the value of ut at t is equal to 0. Then Laplace transform of this step signal is equal to fs, which is a upon s. Then we have ramp signal. Ramp signal is what? It is a straight line. So ft is equal to at for t greater than 0, and for t less than 0, here ft is 0. This a is usually the slope of this line. In Laplace transform, fs is equal to a upon s square. Now the fourth one is the parabolic signal. So parabolic signal is usually denoted by t square, but here we have written a into t square upon 2 when t is greater than 0, and when t is less than 0, ft is 0. In Laplace transform, it is written as fs is equal to a upon s cube. See here, if we consider ft as a into t square, then its Laplace transform would be a upon s cube and then into 2. This is all how Laplace transform works. You will understand while studying the Laplace transformation. So in order to remove this confusion of 2 and to make this similar to the other ones, we have written here a t square upon 2. But you just have to remember that parabolic signal is denoted by t square, ramp signal is denoted by t, and step signal is denoted by 1. And impulse signal is something very different from this thing. So here you can also see that the power of s in denominator is increasing as we go on from step to ramp and then to parabolic, and this is the reason for that increase. When you differentiate the parabolic response, you get ramp response, and differentiating of ramp response will give you step response, and differentiating of step response will give you impulse response. And so its inverse is also true, that integrating of impulse response will give you step response, and integrating of step response will give you ramp response, and integrating of ramp response will give you parabolic response. So you can say that for going from parabolic to impulse, what we do, we differentiate, and for going from impulse to parabolic, what we do, we integrate. Now, as we have discussed, that transfer function of a network represent the ratio of output and input each in the S domain, and assuming all the initial conditions in various elements contained in the network to be 0. This assumption is made by, because here we have used Laplace transform means S domain. You will study while studying the Laplace transfer functions. So you can write transfer function as output in S domain upon input in S domain. And now if input is your impulse signal, then in S domain it is written as 1. And so here the output which you will get will now be called as impulse response. And thus transfer function is also known as impulse response of a system. In question, it is very frequently asked that people refer transfer function by the name of impulse response, but you should not get confused. It is nothing but transfer function. It is not output. See, it is not output. it is basically transfer function. So here you can see that this is output only when the input is impulse signal. It is not the normal output. So now we can say that transfer function is also called as impulse response of the system. Next, we have introduction to compensators. Compensators in control system are used for improving the performance specifications. Steady state or transient characteristics are improved. Basically, they are of three types, which is lead, lag, and then a combination of both, which is lag lead compensator. So here we will first study the lead compensator. Lead compensator is used for improving the speed of the response, means transient state characteristic. This is very important to remember. This is the basic network of a lead compensator. And here this is your input, this is your output, current I is flowing. So if we calculate Vi, means input, then it is equal to current, and then the impedance of this parallel combination plus this R2. So we can write Vi is equal to Is into this. And now what is your output? Output is R2 into Is. So this is your output. And then what is the transfer function? It is the output upon input in S domain. So V0 upon Vi is equal to this. And now here we make some adjustment by taking R1 plus R2 common here. So here we are making this two new terms, T and alpha, where T is your time constant and it is equal to R1C, and alpha is R2 upon R1 plus R2. From here you can see that alpha is less than 1 for lead compensator. So in order to reduce its complicacy, we have written output upon input is equal to alpha 1 plus Ts upon 1 plus alpha Ts. So this is your basic transfer function for a lead compensator. Here you can see that 0 is at S is equal to minus 1 upon T, and pole means this thing. So pole is at S is equal to minus 1 upon alpha T. Since alpha is less than 1, therefore this value would be greater. So we can see from here that 0 would be near to the origin and pole would be away from origin with respect to 0. Therefore 0 will be dominating. Why? Because it is near to the origin. Adding a 0 to a system transfer function in terms of compensator represent a lead compensator. Means lead compensator is equivalent to adding a 0 in the system. So this was all about lead compensator. Now we have this lag compensator. So lead compensator was for improvement of transient response, but in lag compensator, it is used for improving the steady state response characteristic of the system. By steady state, it means elimination of steady state error between input and output. So this is a basic circuit diagram of lag compensator. This is your input, this is your output. Input is what? IES into R1 plus R2 plus 1 upon CS. So Vi is equal to this. And what is output? Output is Is into R2 plus 1 upon CS. So this is your V0, and then we will find the transfer function, which is V0 upon Vi. So this is your transfer function, and here we have made some arrangement. Why? To introduce two new terms again. So this T is your time constant here, and it is equal to R2C, and here we have beta instead of alpha, and you can see that it is having the inverse value of alpha, which is R1 plus R2 upon R2, and it is clearly greater than 1. So we can say that transfer function of lag compensator is 1 plus Ts upon 1 plus beta Ts. So here your 0 is at S is equal to minus 1 upon T, and the pole is at S is equal to minus 1 upon beta T. And since beta is greater than 1, therefore pole is near to the origin. You can see this is your origin and this is your pole, and therefore pole is having the dominating effect. Adding a pole to a system transfer function in terms of compensator represent lag compensator means lag compensator is equivalent to adding a pole, and this was all about your lag compensator. Then we have a combination of both lag and lead compensator, which is lag lead compensator. So here you can see this is your lead compensator configuration and this is your lag. It is used for improving both transient and steady state response characteristics. Why? Because it is a combination of lag lead. It exhibits both lead and lag characteristic in its frequency response. So for lead, we all know that time constant T was R1 C1 and alpha was R2 upon R1 plus R2, and for lag, time constant was R2 C2 and beta is equal to R1 plus R2 upon R2. So the transfer function of lag lead compensator is a product of lead transfer function, which is this, and transfer function of lag compensator. So now from this it is easy to remember the lag lead compensator's transfer function. So for a specific value, if we have this type of representation in S plane, then here you can see that the lag compensator's component are near to the origin. Therefore, in this case, it will eliminate error first and then it will improve speed. Why? Because lag component is near to the origin. But for other cases, when lead components are near to the origin, then it will improve the speed first and then eliminate error. So this was a short introduction of control system. We will continue this subject in further lectures. For any queries, you can comment below. Thank you.